Hey everyone, and welcome to FusionEPtalks. My name is Daniel Medina, and I'm delighted to introduce today's speaker, James Dark. James studied his undergraduate degree in mechanical engineering at Coventry University, UK, then completed a master's in nuclear energy at the University of Cambridge. Then he was first introduced to tritium transport while working in a research position at LSTM in Paris, France. Afterwards, he started as a PhD student at CEA in October 2021, working on modeling of hydrogen isotope transport in breeding blankets, evaluating the influence of trapping mechanisms, neutron radiation, multi-isotope transport, and MSDF. Today, James will explain how tritium transport has been modeled using FESTIM, hydrogen transport code using finite elements methods developed with the FEniCS package to identify the influence of trapping mechanisms on tritium inventories within the breeding plan. Without further delay, I would like to thank everyone for zooming in today. I will now mute myself and hand it over to James. Welcome everyone and enjoy the talk.
Thank you very much, Daniel. Yeah, thanks very much for inviting me. I'm very privileged to be here. So hi everyone, my name is James Dark. I'm a new PhD student at CEA in Cadarache, but also with the University Sorbonne Paris Nord in Paris. And so today I'm going to be talking to you about modeling of hydrogen transport in breeder blankets. And specifically this work is looking at the influence of trapping effects in our studies, basically. So this is obviously something that I would hope everyone here would recognize, the tokamak specifically for ITER. And so during operation of ITER, we're going to have obviously our plasma within the central of within our torus, interacting with our diverger at the bottom here, but in future tokamaks, we would expect that every other spare inch of space is going to be covered with our breeder blanket. And the breeder blanket, the main kind of objectives of our breeder blanket, what we need it to do is we need it to replenish all our tritium fuel supply, and from producing tritium and then removing said produced tritium, we need it to shield all the kind of surrounding components in our tokamak from the neutron damage coming in from our plasma. And we also need the blanket to exhaust all the energy coming in from the neutrons and transferring into heat, something that we can then obviously use to create electricity. So yeah, it's got a lot of jobs, and it'll be a very kind of integral part of future tokamak designs, and specifically for demo. So what other kind of what's the motivation behind doing this kind of research on tritium transport? Well, one, there's obviously safety aspects to consider, like for demo, there's going to be strict tritium inventory limitations on how much tritium you can have on site at once. We obviously were concerned about permeation of tritium going into our cooling channels. There's obviously going to be issues with maintenance and decommissioning if we have tritium on site kind of in the atmosphere, or if it's like lodged in our structure, it's going to create issues with decommissioning in the future. And also hydrogen embrittlement of metals could, obviously, if we're having changes to the mechanical properties of our structural steel as we're operating, then it's obviously a cause for concern in the future. But also just for the performance of our breeding blanket as well, we want to ensure that we know where all our tritium is being produced and where it's going, and make sure that it's going where we want it to go, rather than just kind of diffusing everywhere into our vessel. So yeah, in terms of the project scope of this particular work, so for the past few months, I've been working on specifically studying the influence of trapping effects on the performance of a WCLL breeding blanket, trapping effects of hydrogen in the structure specifically, just because this is something that's not been explored properly in the literature at a macro scale, because trapping effects is something that's a given when looking at material level simulations and much kind of smaller scale. But then when we look at kind of macro component kind of scale simulations or system codes, it's not something that's really kind of taken into account yet. And so this work was just trying to evaluate the importance of them and should they be. So we're going to do this by modeling multi-dimensional multi-material tritium transport using FESTIM, a hydrogen transport code developed by Rémi Delaporte-Mathurin at CEA. And we're going to, from this, we're going to accurately evaluate tritium inventories in our structure Also, we want to evaluate tritium permeation into our cooling channels. And from this, we can hopefully then suggest design alterations so we can mitigate such effects. So how are we going to go about doing this? How do we model tritium transport? Well, we start off with our geometry, obviously. So this is a kind of mock-up of our WCLL blanket for a kind of mock-up for what it could be like for demo. And what we see here is essentially lots of these layers kind of sandwiched on top of each other of these unit cells. And in each case, we're going to have our liquid lithium lead for a water-cooled lithium lead design, where the lithium breeder will kind of flow in from the rear side, coming towards the plasma here, where it'll interact with neutrons coming in, and the flow will go back up and kind of return off to then be processed to recover any tritium and heat. So this is one of the proposed designs for demo. And if we take this like unit model here, and we have a 3D render over here, and then the geometry we use for this work is basically just a 2D slice taken from the central part of one of these 3D models. Now, so this is what we get. So for our WCLL model, we have our lithium lead breeder in green here, which will flow from the bottom up to the top. We have our structural urethra in gray, and our tungsten first wall at the front. And yeah, so identified here. So these are our cooling pipes in the center here, our cooling pipes for the first wall, and our baffle plate in the middle. And yeah, so our plasma will be coming in from this side, interacting with the first wall, and neutrons will be coming in, producing inside the breeder here. And for reference, this model is about 0.5 meter long, and the tungsten's about 2 millimeters thick, from what I remember. And yeah, so this is a kind of example mesh that we would use. Obviously, when looking at the tritium transport, we're kind of most interested in the kind of behaviors of what's happening in the structure. So that's where we have our densest mesh here, all around the structural sides. So this is, yeah. So when we're modeling breeder blankets, it's a very difficult kind of task because there's so many different physics at play. And so you have to consider what physics are you going to consider and how do they interact with each other? Because obviously neutronics is kind of the cornerstone of all simulation to do with like fusion reactors, and WCLLs in particular, because the neutronics is going to determine our tritium source for our tritium, and it's also going to determine our source term for our heat as well, as the neutrons are coming in and interacting. And obviously our heat transfer and fluid dynamics are very tightly intertwined, with heat transfer affecting densities and advection moving heat around. But then both our fluid dynamics and our heat transfer both directly affect our tritium transport, as heat is kind of, obviously our diffusion terms and everything are completely dependent on temperature, and our fluid dynamics is going to be determining the tritium that's being advected away as the liquid breeder is kind of carried around the circuit. But obviously there's all these other kind of physics, as well as many others that haven't been included on this, and these all interact with each other in various different ways. But at some point we kind of have to just decide, okay, at what point we're going to make certain assumptions of, like, are we just going to model in a certain way? But in terms of, for this work, just what's seen in black lines not dotted is what's been considered. So the tritium transport, heat transfer, and fluid dynamics. So what are our governing equations for this? So we have our heat transfer here, our heat transfer term here, including an advection term, and our fluid dynamics using the FusionEPtalks approximation, noting as well that we solve our fluid dynamics and our heat transfer in steady state, and then we project the results of these onto our tritium transport model, which we then use. And so this is how we model our tritium transport using macroscopic rate equations. These were first kind of, such kind of equations were first kind of developed by McNabb and Foster in the 1960s. And from these, we can basically show how the tritium transport is essentially affected by trapped concentrations of hydrogen. And so we have in here, we have our mobile population of hydrogen CM and our trapped population of hydrogen CT, with our diffusion term, source term, advection term, coupling from the fluid dynamics, and how our trapped concentration of hydrogen changes. So for our source terms, we basically just took neutronics data from the literature. So this is for the same WCLL model that I showed before. This is using the same kind of geometry. And this is showing the nuclear heating data as a function of distance from the first wall. So if you imagine this is right next to the first wall here. So we have our kind of tungsten for the first bit, but this is showing the nuclear heating in the lithium lead breeder in green and the structural urethane in blue, and as a function of distance. And then we basically just do a kind of simple fitting of this data, and these equations of the decreasing exponentials basically form our heating source term for each of these materials, for the liquid breeder and for the urethane. And for tungsten, though, we took a value from the literature, which is, and our tritium source term is also taken from the literature, although it should be noted that this source term has actually been evaluated from the same original neutronics work from Morrow here. So it's all for the same model, so we can use them together absolutely fine. In terms of material properties, the biggest thing we're kind of concerned with in hydrogen transport in general is the diffusivity and solubility of hydrogen isotopes in a given material. And these are generally kind of follow an Arrhenius law and are very much dependent on temperature and generally kind of evaluated experimentally. And so we take these from various different sources. And together these two factors form the permeability of hydrogen in certain different materials. It's a function of the two. These are our trapping parameters for each one of our materials, noting we don't have any traps for lithium lead because as a liquid, it can't really get trapped inside the liquid, not in the same manner anyway. So we consider 2 different traps for tungsten and 1 trap for urethane. But although this is a table, kind of a cardinal sin in presentations, we see that's important to look at are these energy values. So these are our detrapping energy values for each trap considered, and also considering the fact that our trap densities are much more significant for tungsten than they are for urethane. And so we only consider 2 traps. We only consider these traps in particular just for simplicity and computational cost. It has been argued that in the literature that there are multiple traps for every material, like for these, like for example, there's sometimes 3 traps for tungsten and sometimes 2 or 3 traps for urethane as well. But for every trap that you add, it's an extra degree of freedom. So it just kind of massively increases your computational cost as you keep on adding more and more traps. In terms of our boundary conditions for a model, for the tritium transport in particular, we consider a recombination boundary condition at the coolant interfaces. So in this case, it'll be water at nuclear conditions. So it's like what, 155 bar and 300 degrees or 15.5, I'm not sure, and 300 degrees C. We consider just a symmetrical boundary condition on the top and bottom, as we're going to be having multiple ones of these on top of each other. We have an implantation flux coming in from the plasma, and for each material interface, i.e. between our tungsten and our urethane and between our lithium lead and our urethane as well, we consider the conservation of chemical potential, which basically just determines that how the concentration of hydrogen changes is basically to do with the relationship of the mobile population over the solubility of a given material. And so this is basically conserved at all material interfaces. And these are also values used for each one of these values, if you're interested. So moving on to some nice results. So obviously, like I said before, where we model the steady state temperature field, this is obviously difficult to do for a 2D model because we have these channel cooling pipes that go along our channel, which we can't really consider in a 2D heat transfer simulation. So what we do is we just do the heat transfer simulation in 3D. And from this, we can then take a central slice from the middle, and that's what we use as a reference to kind of account for all the cooling that's occurring all the way along our channel here. And in this kind of steady state simulation, we have maximum temperatures about 786 Kelvin in our tungsten, 823 in our urethane, and about 925 Kelvin in our liquid lithium breeder. So this is our steady state temperature field. For our steady state velocity field, we can see here now is the direction of the flow coming from bottom to top, with a kind of more kind of uniform flow in our channels and a bit more kind of turbulent within, or a bit more all over the place closer to the front. And if we take a kind of slice here to look at our profile going along these channels, we see this kind of stereotypical like U-shaped velocity curve with maximum velocities of about 0.2 millimeters per second. Because it's a molten salt, it's, well, liquid metal rather, it's not particularly fast. And we obviously see our lowest velocities closest to the wall. Noting, of course, that in this work, MHD hasn't been taken into account. But when you do take it into account, you actually see a much more interesting velocity profile. It's more of a kind of M shape with like more, with a much faster velocities kind of closer to the walls. It's an interesting one. I haven't implemented it in this work for now, but I do hope to in the future. But yeah, it kind of does create a very interesting velocity profile for those who know the work. Yeah, and then so we take the results of these steady state heat transfer and velocity profiles, and we project them onto our tritium transfer simulations. And this is what we get. So this is kind of showing our time. This is the tritium being produced in our blanket, and it's being carried away. So our velocity is kind of coming in from our bottom and carrying all the tritium away. And what we see here is the low. So we see the highest concentrations of tritium where the velocity is minimized. And also we can see here where the tritium is being kind of diffusing into the structure as well. And this is our steady state. This has just been blown up for visualization of the colors. But we can see here where we have our highest concentrations around the middle, and we have a kind of clear lack of tritium here where it's all being kind of carried away from the flow of the liquid breeder moving around. But also bearing in mind, to get up to steady state is kind of a fairly significant amount of time, longer than what would be operational of demo. And then most importantly, when we look at kind of inventories in our structure, we see that including trapping mechanisms is vital really, because we see an increase of tritium concentrations, like our inventories increase by about 15% on average as a whole. Like our total inventory increases by 15% when we include trapping mechanisms, showing that actually with a lot of these kind of macro scale simulations that we do, it's kind of the inventories that they're producing kind of falling into safety guidelines with actually could be quite heavily underestimated. And these inventories can then increase with number of traps and stuff. And obviously, as we can see here, where before there was the much more significant number of traps, the trap density is much higher in our tungsten, which is why we see a much more significant difference here in our tungsten first wall. Also, when we're looking at our first wall in particular, so we have these like first wall cooling channels. So this little GIF is showing our trapped concentration of hydrogen just in our structure, rather than just kind of getting rid of this. And what we can see here is that the trapping concentration is very much a product of our temperature. So what we can see here, where our temperatures are highest, we see the lowest levels of trapping. And that's because the temperature is kind of imparting enough energy onto the hydrogen so that it can escape from these energy wells. And so it can escape the traps and kind of continue diffusing over. And going into our potentially like kind of permeating into our cooling channels as well. But what's also interesting is that when we actually blow up this initial front wall thing, we blow up the colors even more, we can actually see that if we're looking at the hydrogen that's coming from the plasma and what's coming from the breeder, we can see here that the flow of tritium that's going into our cooling channels at the front is completely dominated by the tritium that's coming in from our breeder. And we can see it, like, these are some actual numbers that you can use for comparison. We're seeing here that it's almost like 3 orders of magnitude higher, the quantity of tritium that's coming from our breeder rather than what's coming from our tritium, what's coming from our source from the plasma and diffusing through the tungsten. So it just kind of shows with some models, they try to take into account the tritium that's coming in from the plasma, but in reality, they should really only be considering what's coming in from the breeder in particular. Also looking at the tritium that's going into our cooling pipes here in the breeding zone, we can see I've kind of split the pipes into 3 different sections, our middle, front, and rear, where, yeah, we have them here, and our first wall cooling channels here also in black. We can see here that as the flow of lithium lead is coming from our bottom up here, it's kind of creating these kind of vortexes in the middle. And so we see the highest concentrations of tritium around the central part of our blanket, or middle part of our breeding zone here. And so that's why we see the highest concentrations of tritium surface flux into these middle cooling channels. We also see here that we have very low levels of surface flux of tritium going into our cooling channels in these 4 rear pipes. And that's generally just because the velocity is so much faster here. So it means that there's not as much time for the tritium to diffuse over into our cooling pipes, because all the tritiums, or the majority of it, is being advected away in the current of the flow, kind of moving along. And moving on. So yeah, something else that is that we wanted to study as well. We did a little parametric study on looking at this, because there's this material parameter that we use, the solubility of hydrogen in various different materials. And these values, they can't be determined analytically. They have to be evaluated experimentally. But the problem is, with the solubility of hydrogen and lithium lead, there's such diversity across the literature. It means basically, depending on which reference you use, your results could completely change. And for example, this is the solubility of urethra that we use in this work. So basically, depending on which reference you use for your solubility of hydrogen and lithium lead, at various different temperatures, your hydrogen could be more soluble in your urethra or less soluble, depending on which reference you use for your lithium lead. So we basically did a small parametric study, kind of taking 2 maximum values of our solubility of hydrogen and lithium lead, and picked some values in between, ran simulations for each one. And these are the results that we see. So this might be a bit confusing, but basically what this graph is showing is that as the solubility of hydrogen in lithium lead is increased, we see a much lower level of tritium in our structure. So as we increase the solubility, the hydrogen is more kind of keen and attracted to stay in the lithium lead where it's being produced, and less likely to diffuse over to our urethra structure. And so we see this like massive decline. And bearing in mind, this is our standard case of solubility that we use in the rest of the work. So depending on what value or depending on what reference you use for your solubility, for the majority of other references, your inventories could actually be magnitudes higher. And so what we see here is that depending on basically which end of the spectrum you take, there's a potentially factor 25 difference in your structural inventories of tritium in your structure, and a potentially factor 3 difference in your cooling channel surface flux as well. And yeah, we don't see a change in our tungsten inventory here, because obviously we're not changing the solubility of urethra or tungsten, and our boundary condition is determined by the conservation of chemical potential. So that's why we don't see any change in our tungsten inventory here. But yeah, so where do we go on from here? Hopefully with the rest of the PhD, I'd like to be able to introduce further kind of improvements to the model. So something that we're working on at the minute is neutron damage induced trap creation. So as neutrons are kind of interacting with our structure, it's bombarding the lattice, it's kind of creating loads of defects everywhere. And so this is going to increase the number of traps over time with our model. So at the minute where we just kind of assume a steady state number of traps, which is associated to a material, actually this number could massively increase over time due to the neutron damage over time. Obviously, like I said before, MHD is something that's going to be really important to take into account in CFD to kind of accurately model the velocity profile that we see and the velocity field in the model. Also like to look into more complex interface and surface models, potentially some co-permeation, so kind of accounting for deuterium that's coming from the plasma. And also we'd like to hopefully get a chance to do some experimental validation. Like I know that within the WP-BB package, there's some work, I think by CMAT, for looking at that value in particular for solubility of hydrogen in lithium lead in particular, and doing some more work with lithium lead. So yeah, that's where we go on from here. And yeah, so just in conclusion, FESTIM's been used to simulate tritium transport in both the solid and liquid components of a WCLL breeding blanket. And we accounted for the flow of the lithium breeder by coupling FESTIM to a CFD solve. And so yeah, trapping effects have been shown to be particularly important in the solid parts of our structure, with a 15% increase total tritium inventory in our kind of structural materials. Permeation in the first wall cooling channels is completely dominated by the tritium coming from the breeder rather than from the plasma. And also there's certain material parameters that definitely require some more experimental work on to kind of improve the reliability of the values you use. Because obviously the reliability of models we create are only as good as the values we use from experimental data and stuff. So it's only going to further improve the reliability of our models that we produce. And this work has actually been very recently published in Nuclear Fusion, and I very much encourage you to go check it out if you want to read up more about it or any more kind of specific questions on the work. But yeah, that's me. Thank you very much for listening.
Thank you very much, James, for a very complete talk. I have to say that a bunch of times I just wrote a question and you answered it right away. So it was perfect. So now it's time for questions. So if anyone from the audience has a question, already I see one question from Philip. Philip, so okay, Philip. Go ahead.
Yes, thank you. Good afternoon or good evening. It was a very nice talk. Thank you for your presentation. My question is less regarding the hydrogen and more regarding the simulations you used. Because on slide 15, you get the temperature of the Eurosphere about 800 degrees. Oh, it's in Kelvin. I'm sorry.
Yeah, it's in Kelvin. Yeah. It's like the maximum operating temperature.
Yes.
Yeah.
Okay, so my question is now obsolete because I thought it's in now degrees Celsius. Sorry.
Oh no, it would be well liquid, but that temperature in Celsius for sure.
sorry for that. Thank you.
That's all right. No worries.
Thank you, Philip, for your question. Okay, I see there is already one question from Guido. So you should be able to unmute yourself, Guido.
Yes, okay. So thank you very much for this nice talk. It is furthermore a very important topic for the future of fusion reactors. So my question is, how specific is your work for the European demo design, and to what extent can it be extended or extrapolated or used for the demo designs of the other ITER partners?
I mean, theoretically, we can use any kind of geometry, like, because this is one of the proposed designs for demo, like the WCLL design for demo. But I know obviously there's more. There's like the kind of helium cooled designs as well as the other water cooled the pebble beds. And so theoretically, we can apply this work, the same method to any design really, and more than just demo as well. And yeah, we'd also like to try and potentially do some other work to kind of account for the pulsed nature of demo rather than just a typical steady state as well. But yeah, we can potentially apply this to all sorts as well as for demo, for other tokamaks, everything.
Thank you.
Thank you, Guido, for your question. Okay, I will take the chance. Yeah, I have one myself. And since you mentioned the different kinds of breeding blanket, yeah, so I'm very interested in this topic, but I'm a bit not an expert. And I remember that there are 4 for different types of
Yes.
breeding blankets,
Mhm.
and I'm very bad with the names. But this one, as you mentioned, is not planned to be implanted in ITER. Like it's one of the two that.
I think they're planning on doing a test module for a WCLL, I think. And then there's the helium-cooled pebble beds, which I'm pretty sure is another candidate. And then there was a dual-cooled one. I think it's like a DCLL. So
Yes,
it's like
yes.
a water and lithium, water and helium rather. But
yes.
yeah, this is one of the proposed designs for that. I don't know if it's the leading design. I think they are kind of leaning more towards the pebbles, just because there hasn't been much experimental work done with this yet. But yeah, I think there's kind of four key designs, but then I think there's two that are kind of in particular they're very interested in for demo in particular.
Yeah. So are you aware if similar work, simulation work is done with the other designs? And could you elaborate a bit on why are you specifically focusing on this design?
We just wanted to start somewhere, so we started with this design in particular. The problem with pebble designs that we didn't kind of initially go for is obviously trying to simulate hundreds of thousands of small little pebbles. It can be a bit of a nightmare computationally to kind of create meshes on every single one. But there are ways that we can potentially get around that, like by potentially kind of simulating what happens on a small patch of it and then kind of applying that to the whole domain. But yeah, we just went with this one in particular just because there was no particular reason, just because it was one of the we just saw it was one of the leading designs, so we were like, okay, we can start with this. Looks interesting.
Okay, perfect. And do you see if similar work is done on the other?
Yeah, there has been there is a lot more work recently kind of coming out on tritium transport and breeding blankets, but the major focus at the minute is trying to focus on the velocity fields and looking at the influence of MHD effects, basically.
Yeah,
that's been a kind of key. That's the kind of the current frontier of tritium transport for breeding blankets in particular. But the problem is there is still quite a bit of variation in the results that you see as well. Like people, like it's still, because it's still so new, we're still trying to, like, there are some benchmarks that have just been coming out very recently as of the date of this video for kind of modeling of MHD effects in breeder blankets. And it's very exciting. It's very good. But this work is kind of a bit more unique in the fact that because we're kind of starting from the ground up, we can account for different mechanisms and stuff, and we can couple other physics together very easily because we're not kind of constrained to a particular software like COMSOL or ANSYS or something, because this is all done in FEniCS, which is a kind of open source, well, it might not be open, FEM package. So yeah, it's been a lot easier to use that way.
Okay, thank you. And maybe a second question. I think you were surprised too, but I was very surprised about your result that actually most of the tritium is coming
from the plasma, from the breeder rather.
From the breeder itself.
Yeah. It's I don't know if I can put this on. It's quite nice. Quite nice gift as well. Yeah, it's completely dominated. And this, if you remember from the beginning, so we have a kind of influx of 1e to the 20 tritium per meter cube coming in from the plasma, and still like, because this is due to a few different things. One, the actual contribution is a bit lower, but also the trapping is so much more dominant in the tungsten as well, that there's still quite high concentration at the surface, but because it's so much of the population is being trapped, it's not necessarily all kind of free flowing. But so it's a combination of those factors, that there's more significant trapping in the tungsten, but also because there's just a much higher population of tritium coming in from the breeder rather than what's coming in from the plasma.
Yeah. Yeah. And is there a strategy to try to mitigate this problem? Because
Yes.
along your talk, I was thinking, okay, maybe for this the solubility of the material is kind of good, but only in this direction, because actually you really want the tritium transport to be as efficient as possible in the different directions, right? So what is the strategy here?
Permeation barriers. So the idea is that you're essentially on the surface or the outside surface of your, or potentially on both of your urethra, you'd essentially kind of either spray on or basically have like a material that's a few micrometers thick that would essentially try and mitigate as much permeation as possible. But then, so this could be a material such as like aluminium oxide. I think there's been a few other suggestions. And actually, linking back to the MHD studies, there's actually been some suggestions, because where you have MHD effects due to the kind of electrical potential, or the effects between the lithium lead and the urethra, it's actually been suggested that what insulators they would need to use to mitigate the MHD effects would also actually mitigate a lot of tritium permeation as well. So it could actually be a kind of double-edged sword in that effect. And that's actually something we want to start. That's again something that's kind of very new in the literature, and it's something that we'll be working on very soon as well. Kind of looking at, okay, so this is what it looks like there, but if we start introducing permeation barriers, how does this change things? So essentially just means that your tritium is more inclined to it just stays in your breeder rather than diffusing over.
Yeah, and maybe a follow-up questions about this, especially for these kind of insulators. So they will trap the tritium, but what happens with the material activation in this sense? Or if you did, because also here in Europe, it's very critical, the material activation policy. So will you...
Activation is in from the neutrons, or?
Yeah, material activation, and also if the insulator is just trapping the tritium.
The insulator won't trap the tritium. The insulator will just kind of mitigate permeation. So it'll have like a very, very low solubility to the point where it's just like the tritium it won't kind of be, for lack of a better word, persuaded to diffuse over. Like it'll be more inclined to kind of stay within the breeder itself.
Okay.
Because, so it's just going to mitigate the transport basically, rather than kind of just trapping loads in the insulator.
Yeah, I see now. And what about the neutrons that you were commenting? Will you plan to do some material activation, also modeling, or?
Not necessarily material activation, but just looking at the fact that as neutrons are kind of coming in from your breeder, coming in from your plasma, neutron damage is something that is going to be very significant in the tritium transport world, because traps are essentially just formed from, I think I actually had a slide on it here, like traps are formed from basically different microstructural imperfections, so like different voids, kind of interstitial sites or vacancies, etc. So obviously as your neutrons are kind of blasting in from your plasma, it's going to be massively increasing the number of these imperfections, and thus increasing the density of traps available as well. So it means that, because obviously every material kind of has its standard rough, like a kind of number of traps per meter cubed or whatever, like the standard trapping density, which are just kind of associated with the imperfections. But as your neutron damage is coming in, it's just going to be massively increasing the number of these trapping sites over time. And what else we would expect to see is that obviously the neutrons aren't going to be affecting everything the same. At the front, there's going to be a lot more damage compared to the rear. So we'd actually start to see much more traps being formed at the front. And so we might see more hydrogen being trapped at the front. Because that's something that we're working on at the minute, and hopefully gonna do some nice work on soon. But in terms of material activation, not too much.
It's more about the material damage. Okay.
Exactly.
Yeah, made complete sense.
Oh.
Thank you. Guido, is your hand raised because okay, there is. I don't see. Well, I see a new question from Philip. So you are able to unmute yourself now, Philip.
Yes. Okay. Great. Thank you. When my question is regarding the solubility of tritium in lithium lead.
Yes.
Why do you think there is so wide range of results?
I think it's largely due down to the experimental technique used to kind of get these values. Like from what I remember, they're either done from adsorption or desorption, and obviously some of these values were taken quite a few years ago. There's basically a whole range of techniques used, but then also we're talking about the solubility of hydrogen in a liquid, whereas like most other values that we have for like the solubility of hydrogen are in solid components, like in our tungsten or iron or urethane. So it's a lot easier to obviously work with a solid sample, but with a liquid metal, it's so I guess there's so many more factors at play that it's kind of difficult to measure these values in a kind of controlled manner. But I know this is definitely something that's actually, like, for anyone who's actually done some work or knows of work in the tritium modeling space in breeder blankets, this is actually something that's kind of, it's a bit of a broken record now. Everyone's kind of doing this same kind of study of looking at, and this uncertainty has been looked at a lot, and it's now something that there has been funding to kind of do some more work to get design a new experiment to kind of finally come up with a more reliable value for solubility of hydrogen in liquid lithium lead.
Okay, thank you.
Guido, do you have a question?
Yes.
Okay.
At the end of your talk, you mentioned some future experimental work. Can you tell something more about it?
Oh no, this is it's so I'd like to, because basically a model is only useful like once you've been able to experimentally validate it, right? So like we haven't got anything planned at all really, but it's just something that we'd like to be able to do, like maybe some experimental validation regarding tritium permeation barriers, for example. That's something that I mentioned with before, because that's something that we've started to kind of try to model, but at the end of the day, until we've done some experiments to kind of replicate what we're doing in these models, then we don't know if these models are actually correct, right? We don't know if they're actually replicating what's happening in real life. So yeah, it's something that we hope to be able to do at some point to kind of actually validate the work, but it's not anything that we've planned yet. That's all.
And would this be done at Cadarache or in Karlsruhe or?
Hopefully anywhere really. I think if we could work with anyone, like but in terms of work at Cadarache, I know that there is a lot of kind of tritium permeation studies that we are doing at Cadarache, particularly the work of like within the IRFM lab as well. And so yeah, so we have some in-house experiments that we could potentially work with, but nothing is planned at the minute.
Thank you.
Okay, thank you, Guido, for your question, and James for the answer. I don't see any more questions from the audience.